Today we will be solving this problem called counting towers. So our task is to build a tower whose width is 2 and height is n. We have an unlimited supply of blocks whose width and height are integers. For example, these are possible solutions for n equals 6. So we will be given n and we need to find how many different towers we can build. Mirrored and rotated towers are counted separately if they look different. So we will need to answer many tests. So the first line will contain an integer t representing the number of tests. Then each line will contain an integer n that can be as large as a million. And we need to output the number of possible towers modulo a billion and 7. So let's go to the drawing board and try to come up with an answer. So as we saw in the example, the answer for 2 is 8. So for starters, let's enumerate the 8 possible configurations when n equals 2. Maybe that will give us some insight into solving this problem. So as you can see here, these are the 8 possible configurations. And this one, for example, is not valid because this block is not a rectangle with integer width and height. So these are the only possible configurations. Now let's go back to the picture showed in the problem statement. So as we can see here, these are 4 possible configurations when n equals 6. And the first step that seems logical in solving this problem is making sense of these configurations. And what I mean by that is finding a way to encode these configurations, because we will need to differentiate the different kind of configurations so we will be able to count how many there are. And in order to do that, we need to encode these towers in a sensible way so that we can compare them programmatically and make sense of them programmatically. So the first idea that comes to mind is to encode the number or the height of the blocks in the left part and the height of the blocks in the right part. So I could encode this left tower with 6 ones because it has 6 blocks of ones. And the same will apply to the right tower. So there are 6 blocks of ones. But if we try to apply this to the third example here, we will get the following. So we have 1, 1, 1, 2, and 1. And for the right tower, we would have 1, 2, 2, and 1. But here we don't know if this part is connected or not, because we couldn't encode for that in our configuration here. So for all we know, this part can be connected or it can be not connected. So using this type of encoding is not enough to get all the informations of these configurations. So this is not enough. We need to come up with something better. And before I present the way we're gonna encode these configurations, I invite you to pause the video and think about it for a second. So here we go. As we said earlier, keeping track of the number of blocks in the left and right part is not enough because we lose the information about the connections between the two blocks. And if we take that into consideration, we can see that keeping track of these intersections is enough to get all the information we need about our tower. So I'm gonna go ahead and pinpoint all these intersections. Since these towers are of height 6, they're gonna have 6 intersections. And now all what we need to do to encode this tower is to look at the type of crossing we have at each intersection. And these type of crossings are precisely the 8 we just saw here. Since each crossing represents a tower of height 2, then it can be only one of these 8 types. So I'm gonna go ahead and give numbers to these towers. So this is gonna be 1, 2, 3, 4, 5, 6, 7, and 8. So tower 1 here can be encoded in the following way. The first intersection here is of type 1, then 1, then 1, then 1, then 1, and finally this intersection is of type 3 because it has only this part. The upper part is not present, so it is of type 3 here. And now moving on to the second tower. So the first intersection is of type 4. The second one is of type 4 as well. The third one here is just a perpendicular line, so it is type 6. Then the next one is of type 4 again. Then type 4. And finally this one is of type 3. Moving on to the next tower. The first intersection here is of type 2. The following one is of type 4. This one is of type 3. The next one here is actually just an empty box, so it's of type 8. Then the following one is pointing up, so it looks like 2. And the last intersection here is of type 3. And finally the last tower here has all these empty blocks here, so the first intersection is of type 8, and so is the second and third intersection, whereas the fourth one is a T looking up, so it's of type 2. Then the next one is of type 1, and finally the last intersection here is of type 3. And what's amazing about this is that if you give me this array here, I can reconstruct my tower really easily. So we've accomplished our first goal, and that is of encoding these towers. Now let's move on and see how this encoding will help us in solving our problem. So let's continue. Now we'll try to find some towers of height 5, and these are our 8 possible crossings. So let's go ahead and fill our tower. So for this first intersection here, we can pick any crossing we like. So say we pick crossing number 1. So this would look like this. And now for my second intersection here, I would like to pick the 7th crossing here. So I would go ahead and throw it here. But is that valid? Can I actually pick crossing 7? And the answer is no, because there is an overlap between the first crossing and the second crossing. And since the first crossing had this part on, the crossing I'm gonna pick for my second intersection here has to have the bottom part on, otherwise they won't be able to match. Because if I go ahead and put 7 here, then when encoded this would look like 1 and 7, but so will 1 and 3 here. 1 and 3 will also look like this, and since our encoding needs to be 1 to 1, this is not possible, and we implicitly stipulate if two intersections are following each other's, the crossings we pick need to be complementary. So if we pick 1 here, we can only pick crossings which have their bottom part on for our next intersection. So we should create a table that indicates which crossings are possible from any given state. So I'll start by having my current state here, and there are 8 possibilities. And next I will have my next state, and it also has 8 possibilities. So my current state is 1. What are the possible crossings that I can have for my next state? As we said, since the top part of 1 is on, the following configurations needs to have the bottom part on. And what are the crossings that have the bottom part on? 1 has the bottom part on, and so does 3 and 4 and 5 as well as 6. So we need to link 1 to 1 and to 3 to 4 to 5 and to 6. So since I picked 1 for my first intersection, I can only pick one of these for my second intersection, and I will pick 5. So my next intersection will look like this, because 5s look like this, and there is an overlap between the top part of 1 and the bottom part of 5. And now my current state is 5, so again, since the top part of 5 is on, my next state should have the bottom part on as well. So here for 5, it's gonna have the same connections as 1. So it's gonna have a connection with 1, 3, 4, 5, and 6. And I can pick any of these to be my next intersection, and I will pick 3. So I'll go ahead and draw 3 on my tower. See, 3 has only this bottom part that's gonna overlap with the top part of 5, and that's gonna be pretty much it. And notice that 3 does not have the top part on. So now my next state should not have the bottom part on. So what are the possible states that can be linked to 3? They are precisely all the states that do not have the bottom part on, and these are 2, 8, and 7. Exactly those that are left here. So I'll go ahead and link these. So 3 will be linked with 2, 7, and 8. So I can pick any of these for my next intersection, and let's say that I pick 2. So it will look like this. And notice here that there is no issue here because 3 did not have the top part on, so 2 does not have to have the bottom part on. Now I am at my final crossing here, and since 2 had the top part on, I can only pick from those states who has the bottom part on, and these were, as we saw, 1, 3, 4, 5, and 6. But I have one more constraint here. Since this is my last intersection, and since my tower has height 5, then there shouldn't be a top part to this intersection. Otherwise, it's gonna exceed my height of 5. So I can only pick an intersection if it does not have the top part on. And out of the intersections that I mentioned, 1, 3, 4, 5, and 6, so 1, 3, 4, 5, and 6, only 3 does not have the top part on. So that's my only choice here, and it will look like this. And there is an overlap here between the top part of 2 and the bottom part of 3. And this way, my tower is finished. If I were to pick 1, 4, 5, or 6, there is gonna be a top part sticking out here, and that's not permissible. So we just noticed something very important here. Our last intersection should not have the top part on and should be completely closed here. And the only crossings that satisfy these two conditions are 3 and 7. So now I know that my last crossing should be either 3 or 7 for last crossing. So all the pieces of the puzzle came together now. We encoded our tower in this manner, and this allowed us to have states, and we found a way to transition between states, and we found a constraint for our final state. So these are all the prerequisites for a good dynamic programming approach. So all what we have to do now is to clarify the steps before moving on to our code. So our dynamic programming will be two-dimensional. The first dimension here will go from 0 to n, which represents which crossing we are at. And the second dimension here will go from 0 to 8 to represent the 8 possible configurations that we have here. And at the beginning, we're gonna start by initializing the first intersection here, and it can be any of these states because there is no reason any of these states cannot be possible. So we're gonna start by stating that dp of 0 of all values from 1 to 8 is just equal to 1, meaning that if we only had a tower of height 2, then there are 8 possible configurations for it, and those are precisely the ones we mentioned. And after the initialization here, we need to move on to the next step. So if we are at some position I and we need to find the number of towers that have the crossing j at position I, we need to know how we could have gotten to this position here. And in order to do that, we need to have the opposite transition here, meaning if we are at a given state, we need to know which are the states that we could have came from. So basically, if our next state is 1, this means that we have the bottom part on, so we must have came from a state that had the top part on. So we could have came from 1, 2, 4, 5, or 6. So that's why dp of ij, for example, dp of I1 will be equal to dp of I minus 1, 1 plus dp of I minus 1, 2 plus dp of I minus 1, 4, 5, and 6. Because we could have came from all these states and we could have just added this crossing to the next state. And we're gonna have a similar situation if our current state here is like 2 and does not have a bottom part. So the state that we came from here to 2 should have the top part off, and the states that do not have the top part on are 3, 7, and 8. So that's why dp of I2, for example, will be equal to dp of I minus 1, 3 plus dp of I minus 1, 7 plus dp of I minus 1, 8. And we will go ahead and do that for all i's from 0 to n if you go 0 indexed. And our final answer will be read from only state 3 and 7. Because when we get to this position here, we said that we have to finish with either state 3 or 7, so we don't have anything sticking out from there. So at the end, we will just output dp of n3 plus dp of n7. And that will be our final answer. And for complexity here, we will go through n states, and for each state we will need to calculate its dp value from either 5 or 3 previous states, and this is constant in a sense because we just perform either 4 or 2 additions here. So our total complexity will be O of 8 times n, which is asymptotic to O of n. And in order to answer all the queries, we shouldn't calculate the dp each time up to n, so we will go from 0 to the max n in the beginning and save all the answers. Then we will process the t queries, answering each one of them in O of 1, since everything would have been calculated beforehand. So that's pretty much it. Let's go ahead and check out our code now. Okay, let's check out our code now. So this is our program. I'll start by defining two constants here. So I'll define next to be the maximum value of n, and I will set that to a million plus 10. And I will define mod to be my modulo, because remember we need to calculate the answer modulo a billion and 7. Then I will move on to calculate my dynamic programming, and in order to do that I will declare a vector of longs that I will call number of towers, and it will be of size next, and its second dimension will be of size 8, and I will initialize everything with 0, because remember here we said that our DP will be the first dimension will be of size n and the second one will be of size 8. So moving on, I'll start by doing my initialization here, and as we said, the first intersection here can be anything, can be any states from 1 to 8. So dp of 0 of 1 to 8 can be 1. So I said that here. So for all values from 0 to 8, number of towers of 0i is equal to 1. Next, I will move through all the values from 1 up to next, and for each one I will perform the transitions we just talked about. So for each state I need to calculate the number of ways of reaching that crossing. So in order to do that, I will need to loop through all 8 configurations. So I do that here. So for j equals 0, j less than 8, j plus plus. And here I will have two cases. The first case is, as we saw, is if my current state has the bottom part on. So if it has the bottom part on, it must have came from a crossing that had the top part on. And the crossings that have the bottom part on are 1, 3, 4, 5, and 6. And since we are taking them 0 index, they would be 0, 2, 3, 4, and 5. So if j is equal to 0, 2, 3, 4, or 5, this means that we could have only gotten to this state coming from a state that had the top part on. So that's why we will need the number of towers of ij will be equal to the number of towers of I minus 1 for all configurations that had the top part on. And if we look here, the configurations that had the top part on were 1, 2, 4, 5, and 6. And 0 index would give us 0, 1, 3, 4, and 5. And that's precisely why we add 0, 1, 3, 4, and 5. So these are all the configurations that had the top part on. And now our second state, which corresponds to having the bottom part off. So if we have the bottom part off, as it is the case for 2 or for 7 and 8, then we must have came from a state that had the top part off. And we only have 3 such states, which are 3, 7, and 8. And 0 index would give us 2, 6, and 7. So else, the number of towers at ij will be just the number of towers of I minus 1 of 2, 6, and 7. So that's pretty much it. That way we calculated all the number of towers. Now we can process our queries. So we'll start by reading T, then we will process the queries here. So we need to read N, and then as we said here, the answer for each N will be just the number of ways of reaching configuration 3 or 7 in the last intersection here. So for each N, the answer will be just dp of n minus 1, 3 plus dp of n minus 1, 7. And since our program takes these configurations more in 0 index, so the answer would be dp of n minus 1, 2 and dp of n minus 1, 6. So that's why we just print the number of towers at n minus 1, 2 plus the number of towers at n minus 1, 6 modulo. And that's pretty much it. So let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.